Okay, hello everyone. So today's topic is magnetic field due to toroid. So what we'll do is we'll first understand what is the meaning of toroid, then what will be the magnetic field due to toroid. We'll derive the magnetic field using Ampere's second law, and then we'll solve a numerical. So this is how a toroid looks like. Okay, so let's discuss first the definition of toroid. So what is a toroid? So toroid is a hollow circular ring on which large number of turns of a wire are closely wound. As you can see in the figure, it can be viewed as a solenoid which has been bent into a circular shape to close on itself. So if we take a solenoid and if we bend the solenoid to give it a circular shape, then it will turn itself into a toroid. So a solenoid when bent itself in a circular shape will form a toroid. So this is how a toroid looks like. Okay. Now magnetic field lines due to toroid. Now remember one thing. Due to a toroid, magnetic field will be only inside the core of toroid. The magnetic field will not be outside the toroid or in this region of toroid. We'll prove it how it is possible. But remember, near this axis, the blue colored line, as you can see, the magnetic field due to toroid will be uniform near this axis. And what will be the value of that magnetic field? We'll be deriving with the help of Ampere's second law. But remember, there will be no magnetic field outside the toroid or in this region of toroid. There will be magnetic field only inside the core of toroid, and the value of magnetic field will be uniform. Okay, and what will be the value, on what factors will it depend? We'll discuss in the upcoming slides. Okay, so first we'll find magnetic field at this point P. So suppose I make a small circular loop L1 here, and I put Ampere's second law, that is integration of B dot dl for loop L1 equal to mu naught I enclosed. Now as you can see, in this black colored smaller loop there are no wires. Wires are here. This white colored are the wires. So there is no wire in this loop L1. So I enclosed is 0. So magnetic field will be equal to 0. So in this region, the magnetic field will be equal to 0 because current enclosed is equal to 0. Now suppose I take a loop L2. The size of loop is more than the size of toroid now. Now as you can see in the figure, as you can see, the current is entering from this wire. So at this point the current will be inwards and the current will be outwards at this point. Again inwards at this point, outwards at this point, because the current is flowing like this. So at this point the current is inwards, then at this point the current will be outwards. So again inwards, outwards, inwards, outwards, at this point inwards, at this point outwards, at this point inward, at this point outwards. So as you can see, the total number of times the current is inwards is equal to total number of times the current is outwards. So suppose the number of turns is n. So the total number of current that is going inwards will be minus Ni. Similarly, the current is coming out also and same number of turns. So total number of current that is coming outward will be plus Ni. So again the I enclosed will be equal to 0 because the total current inwards is equal to total current outwards. So I enclosed is equal to 0. So magnetic field B2 will also be equal to 0. So even in the region outside the toroid, in all this region value of magnetic field will be equal to 0. Because if I form a loop here, then the total inwards current, the current going inside the paper or inside the plane is equal to total outwards current. So inwards current is negative, outward current is positive. So net current enclosed will be equal to 0. So magnetic field will be equal to 0. Now we'll discuss magnetic field at this point P. Now this point P is inside the core of toroid. This point P is inside the core of toroid. Suppose I is the current, N is number of turns and R is radius. Radius will be A plus B by 2 where A is the inner radius, B is the outer radius. So R will be average of both of them, that is A plus B by 2. And suppose now this black colored loop, if you can see there's a black colored loop L3 and I take a point P on the loop. So if we'll put Ampere's second law, that is integration of B3 dot dl equal to mu naught I enclosed for loop L3, if you can see the magnetic field will be constant, so it will come out of the integration, and A dot B is AB cos theta, so B3 dot dl will be B dl cos 0 and cos 0 will be 1 equal to mu naught Ni. Now see, If you'll take this loop L3, so if you can see, the current is only going inwards in this loop because from the point where the current is outwards, it is outside of L3. So we'll not take this current, we'll only take the inwards current, and the total invert current will be equal to total number of turns into current, because suppose we have n turns and in each turn the current is I. So total enclosed current will be Ni. So it will be mu naught Ni. So B into 2 pi r will be equal to mu naught Ni because total length will be 2 pi r. So magnetic field inside the core of toroid will be mu naught Ni upon 2 pi r, where small n is number of turns divided by 2 pi r, and where r is given by a plus b by 2. Okay, but remember, we are only concerned about finding the total magnetic field. So I haven't put the sign minus here. I'm only concerned about the magnitude of magnetic field. So the magnitude of magnetic field is mu naught into number of turns into current divided by 2 pi r. And r is basically what? R is average of inner radii plus outer radii divided by 2. Okay, remember one thing. If in question number of layers are given, suppose it is given that there are four number of layers of toroid. So you do what you do is you to multiply this magnetic field with number of layers. Suppose number of layers are given, then you have to multiply the magnetic field with number of layers. So in this region, the magnetic field will be equal to 0. Outer magnetic field will be equal to 0. So magnetic field will be only inside the core of toroid, and its value will be mu naught Ni divided by 2 pi r. And if number of layers are given, then multiply with number of layers. Okay, let's solve a numerical now. So a toroid has inner radii of 25 centimeter, so A is given. Outer radii of 26 centimeter, so B is given. With 3500 turns, so number of turns is given, that is equal to 3500. And current of 11 ampere, and I is given to be 11 ampere. Find the magnetic field inside the core, outside the toroid, and empty space surrounded by the toroid. Now see, the radius will be a plus b by 2, so we'll convert it into meter. So inside the core will be mu naught Ni by 2 pi r. We'll put out the values and we'll get the value. Now if you'll see, outside the toroid magnetic field will be equal to 0, and in the empty space surrounded by toroid magnetic field will be equal to 0. So magnetic field will be there only inside the core of toroid. Okay, now what you have to do is please learn and write down the derivation discussed in this slide. Okay.